All right, so let's continue our discussion about what a transformer is, sort of this introduction to the transformer. I'm taking this figure that was on the first slide and kind of just transferring it over here. And I want to show this one-to-one correspondence with what we're looking at in terms of the practical look of a transformer. And we can see this, piece of wire being wound around for the primary coil. Again, we can label some of this stuff. This is called the primary winding. This blue one is called the secondary winding, and you can think of this as the input to the transformer, and this is the output of the transformer. And you can kind of see how these metrics or these parameters of the transformer sort of map to the actual electrical symbol of the transformer. So when we're looking at electrical circuits, like I mentioned, this is the symbol that we're going to see. We're going to see these two coils, some kind of dot convention, the line indicating that they're wound around the same core. And then typically what we'll see is a turns ratio, this N1 to N2 here. That's called the turns ratio. It's basically the ratio of the number of turns on the secondary. So this is the secondary coil. The number of turns on the secondary to the number of turns on the primary. And so you see that here. Basically, N is the turns ratio, and it's equal to the ratio of the number of turns on the secondary to the number of turns on the primary. And this is going to be very important because this turns ratio will not only tell us the ratio of inductances, so from the turns ratio we can get the ratio of these two inductors, and vice versa. If we have the value of the two inductors, we can easily determine the turns ratio from this equation right here. So let me actually just throw a box around that. This is going to be a really important equation. So if I just give you values for L1 and L2, you should really easily be able to calculate the turns ratio, because basically it's saying that the turns ratio N is equal to the square root of L2 over L1, okay? And so these turns are really important because they tell us how the voltage is stepped up, okay? So we haven't gotten there just yet, but it's the case that V1 over N1 is equal to V2 over N2. And so you can rearrange this to show that V2 is equal to N2 over N1 times V1, right? So the voltage on the secondary, V2, is equal to the voltage on the primary multiplied by this turns ratio. And that's really powerful, because that means that if I make this turns ratio 1 to 10, I can get a voltage at the secondary, V2, which is 10 times V1. So I can really easily step voltages up using a transformer. AC voltages, of course, again, transformers only work for AC. So I want to keep noting that. It's very important that you know that. Somebody might ask you that on an interview and say, hey, what range of frequencies do transformers work for? They work for a wide range of frequencies, but they do not work for DC, okay? It depends on the transformer. Some transformers operate at low frequencies, some operate at high. The bottom line is it has to be AC. You cannot use DC with a transformer, and if we have time at the end of the module, I'll explain why that's the case. But it is the case, okay? And so you see here that we can get really good step-up ratios if we just have more turns on the secondary, and that's kind of what they're showing here. They've got 8 turns on the secondary and 4 on the primary. So, we could write this as 1 to 2 if we wanted to be accurate to the figure. You can just say this is a 1 to 2 step-up transformer, and so the output voltage V2 would be double the input voltage. And we could keep adding turns, right? And you can see that on the first page here, they had more turns on the primary side than they did on the secondary side. So what would happen in that case? Well, in that case, the voltage would be stepped down, because I'd have a turns ratio, N2 over N1, right? N would be less than 1. And that means that I would get a step down transformer, okay? So there's different types of transformers, step up and step down transformers, based on the turns ratio here. And the turns ratio is always given as the number of turns at the secondary divided by the number of turns at the primary. So you'll rarely, if ever, see it written the other way around. Okay? And so as I mentioned, these two lines here indicate that these two windings are wrapped around the same core, which is what we see here. And so you'll know what that means when you see it, right? And then the dots, of course, we've seen this already, and we know how to deal with this. Typically, not going to need to use the dot convention maybe as much for ideal transformers. And when we're looking at ideal transformers, we typically just use the dots to indicate the polarity of the voltage, because with an ideal transformer, we can really easily look at the voltages and just use this, some of these expressions like this one that I wrote here, to determine what's going on in the circuit. We might not even need to look at the mutual inductance in some cases. So like I said before, transformer is really just a special case of what we've already seen, this magnetic coupling, where instead of the coupling being unintentional, it is intentional, and we're placing some high permeability magnetic core into the system where the windings are wrapped around that core, and that core gives us really good coupling. And that's what we want, right? The transformer is basically utilizing this magnetic coupling property so that we can step voltages up and step them down. And this is really practical stuff. So if you have any questions, please feel free to let me know. I'm gonna go ahead and wrap up this video right here, and in the next video we'll start getting into some of the details, getting down into how we're gonna use these in circuits, and then we'll start solving some examples. All right, so I'll end this video right here.